Greetings, everybody. Learning is a hobby here. I want to finish part 2 of the videos of my solutions to some of the exercise sets. Sorry, some of the exercises in chapter 5 of Spivak. So I just want to. There was just a few more problems that I wanted to do that I didn't get around to in the first video for the solutions. So there's only a few more that I did, so I'll just finish up with those here. And I just wanted to mention also, I'm going to try and get the summary for chapter 6, the video for that, filmed and put up on the channel by tomorrow. I don't know if I'll have time to finish that tomorrow, but if it doesn't go up tomorrow, it'll go up on Monday. So just keep an eye out for that. All right, so we are moving along with Spivak here. Let me bring up my solutions for the rest of the problems that I did in chapter 5. There is one little thing I want to start with here, just a small correction for question number 20 that I did towards the end of the first video. I just want to fix an oversight here. I did this proof by cases for question 20, but for the 2 cases that I did, the way that I did it works when the number a is strictly greater than 0, but you could do a similar, an exactly analogous type of thing for the case where a is strictly less than 0. You just have to sort of flip which branch of the curve you're on. So maybe you could. I didn't write it out just because I didn't feel like spending the time to do that, but hopefully if you draw the picture, what I'm saying should make sense. So I just wanted to mention that here. The 2 cases that I did here work when a is positive, strictly positive, right? But technically, we should say something about what happens when a is negative. Okay, so, and then we did 21 in the last video as well, so I'll skip over that, and we'll move on to the last few problems that I did, starting with question 22. So let me read it out. Consider a function f with the following property. If g is any function for which the limit x goes to 0 of g of x does not exist, then limit x goes to 0, f of x plus g of x also does not exist. Prove that this happens if and only if limit x goes to 0, f of x does exist. And he gives a hint here. He says this is actually very easy. The assumption that limit, excuse me, limit f of x as x goes to 0 does not exist leads to an immediate contradiction if you consider the right g. So here's my proof. It's an if and only, biconditional, if and only if. So I did both directions. The first one, obviously, I did with a proof by contradiction using his hint. So here I'm assuming that f is a function for which limit f of x as x goes to 0 does not exist, and pick g of x equal to negative f of x, then limit as x goes to 0 of g of x does not exist, right? Because it's defined in terms of f of x. Then then limit x goes to 0 of f of x plus g of x is equal to the limit of the constant function, the function identically equal to 0 as x goes to 0, which is 0, but that shows that the limit of f of x plus g of x exists, and that's our contradiction. All right, and now doing the opposite direction, I did this one with contrapositive. So now assume that limit g as x goes to 0 does not exist, but that the limit does. For or actually, did I do this with contradiction as well? Assume limit does not exist. No, this is contrapositive. Sorry, because I'm assuming that the negation of the first part. So assume limit g of x as x goes to 0 does not exist, but that the limit of the sum does exist for some L and R. Then limit f of x equals L minus then the limit of f of x as x goes to 0 equals L minus the limit as x goes to 0 of g of x, which implies that limit f of x as x goes to 0 doesn't exist because the limit of g of x doesn't exist. So that shows that the other direction holds. Right. So like I said, that was using the contrapositive for the second part. Okay, next question. Question 24. Suppose that an is for each natural number n, some finite set of numbers in the closed interval from 0 to 1, and that an and am have no members in common if m is not n. Define f as follows. So f of x is 1 over n if x is in the set an, and it's 0 for if x is not in an for any n. And here they want us to prove that the limit of f of x as x goes to a equals 0 for all a in the closed interval from 0 to 1. Right, so here's my proof. All right, so let a be an element of that interval. Choose epsilon greater than 0 and n large enough such that 1 over n is less than epsilon. Then either here in the interval, either the interval a minus 1 over n, comma a plus 1 over n intersected with the union of the sets a sub k, where k goes from 1 to n. Either that's empty or else it's finite, since the union of the AKs where k goes from 1 to n has finite cardinality, right? Because each of the AKs have a finite number of things in them. All right, then if interval a minus 1 over n, comma a plus 1 over n intersect the union of those sets is not empty, choose delta less than minimum of the absolute value of xn minus a, where xn is an element of the union. Otherwise, choose delta less than 1 over n. Then for all x, if x minus a in absolute value is greater than 0 and less than delta, then all the y values here will be in an absolute value less than 1 over n, which we chose to be less than epsilon. So that is the proof. All right, that's 24. Next one is question 40. Like I said, I just chose some other ones that looked interesting to me. So there's two parts. Did I do? Yeah, I did both parts. Okay. There's multiple parts to this one. 40A says find the perimeter of a regular n-gon inscribed in a circle of radius r. So here's the solution. So you hear just from the picture, say this is our circle of radius r, and say we have a regular n-gon inscribed in here, so all the sides have the same length, and all of these sides of these triangles that we get have the same length. It's the radius of the circle. Okay, then all these angles theta here are all the same, right? And so on. So if you look at the particular triangle that I drew here in black, this is my angle theta. I drew the altitude, which I'm calling h. That's this length here. The sides of this triangle are r, and s is the side here, which is the length of the side of the n-gon, right? Of one of the sides of the n-gon. Okay, then just from regular trigonometry, cosine of theta over 2 is h over r, and we can use this to solve for h. Remember, h is the altitude of the triangle, this length here. Okay, then h is r cosine theta over 2, and then just using the Pythagorean theorem, s over 2 squared, which is the same thing as s squared over 4, plus h squared equals r squared. Again, that's just Pythagoras. And here, if I solve for s squared in this equation, I get s squared equals 4r squared minus 4r squared times cosine squared theta over 2. Okay, and then just using a trig identity, s squared is equal to 4r squared sine squared theta over 2, because 1 minus cosine squared theta over 2 is sine squared theta over 2 by the Pythagorean identity. And here, if you take the square root, we get plus or minus, s is plus or minus 2r sine theta over 2. Theta is an acute angle here, so we don't need to worry about absolute values around the sine function. We choose the positive one because s is the length of a side of an n-gon. So then s is equal to 2r sine theta over 2, which gives us the perimeter if we multiply that by n, right? Because there's n of these sides. So P is ns equals 2r n times sine theta over 2. And furthermore, n theta is equal to 2 pi, right? Because there's n sides to this regular n-gon, which means if you go theta plus theta plus theta, n times, you end up back where you started. So in other words, you do one full revolution. So if you add theta to itself n times, then you get 2 pi, or in other words, n theta equals 2 pi. Then that implies that theta is 2 pi over n if you solve for theta. So p is equal to 2r n sine pi over n, and that's the formula that he asks us to derive in part A. It's basically just an application of some trigonometry. Okay, and then part B says, what value does this perimeter approach as n becomes very large? So as n becomes very large, we get closer and closer to the circumference of the circle, which is 2 pi r, as we know from geometry. So here, if you take the limit as n goes to infinity of 2rn at sine pi over n, that's equal to limit n goes to infinity of 2r pi sine pi over n over pi over n, just using some algebra. And finally, in part C, he says, what limit can you guess from this? The limit we can guess is that sine of x over x as x goes to 0 is equal to 1. Right? Something that we already know, but I guess you could use this to guess that. Okay, I think this is the last one that I did. So question 41, part A. Oh, I just realized I only did one part of this. Hang on one second. Is there multiple parts to this one? Or am I losing my mind? Part B said, oh yeah, it looks like I forgot to do part B, which says more generally, if C is greater than 0, approaches 1. I think it's probably very similar to the answer to part B. I'm not gonna do it because I think this one gives you kind of like the idea behind it. So here's 41 part A. For C greater than 1, show that C to the 1 over n power, which is the same thing as the nth root of C. If you just remember your way that the radicals are defined in terms of powers, approaches 1 as n becomes very large. And he gives a hint here. He says, show that for any epsilon greater than 0, we cannot have C to the 1 over n power greater than 1 over epsilon for large n. It's basically just, you can use Bernoulli's identity for this. This is just an application of Bernoulli's identity. So the part B is the case where C is greater than 0, and I think it probably works out almost exactly as this application of Bernoulli identity. Sorry, not identity, his inequality. Sorry, Bernoulli's inequality. So I'll let you look back at that. We talked about Bernoulli's inequality like way back in chapter 2. So, but anyway, I didn't refer to Bernoulli's inequality here, but I'm actually using it here in my last steps. But let me go through how I prove this. So here's the proof. Let C equal 1 plus m for some m greater than 0. Choose epsilon greater than 0. Then if you choose capital N to be greater than the ceiling of m over epsilon, just to make it an integer. If n is greater than capital N, then 1 plus m is less than or equal to 1 plus n epsilon, which is less than, just by the binomial theorem, 1 plus epsilon to the nth power. All right, and then that implies that C to the 1 over n power is equal to 1 plus m to the 1 over n power, which is less than or equal to 1 over epsilon, just by, like I said, from this part here, if you take the nth root of both sides. And that shows that C, the nth root of C is always less than or equal to 1 over epsilon. Since this is true for any positive epsilon, that means that the limit has to be 1. All right. And that's it. So let me actually just stop the screen share here for a second. All right. So like I said, I'm going to move on now to chapter 6, which is on continuity. So we're still sticking with limits, but we're going to use limits to define continuity, the concept of continuity. And looks like there's some interesting problems to do in that section too. So hopefully the summary for that chapter I'll be able to get posted by tomorrow. So look out for that. If not by tomorrow, it'll be up by Monday because I have off on Monday because of the holiday. So anyway, I hope you guys enjoyed the problems that I did choose to do from chapter 5. I enjoyed them. I thought they were pretty fun. Let me know what you guys think in the comments, and I'll see you guys in the next video, which should, like I said, should be coming up within the next couple of days. So keep learning, everybody.